Hi everybody, I'm Bil Herd. I call myself a recovering Commodore engineer. Has anybody heard of Commodore? Thank you. I'm done. So it's funny because these days it's getting harder and harder to find somebody that knows of those days. And I include Atari, I include all those things, except for that fruity company. So today I wanted to talk about why I hate computers. No, what's happened recently is I've been having a lot of people tell me what they would do differently had they been me. And that's interesting, you know, about aging and stuff. And what I'm running into is people telling me, you designed it wrong because it only lasted 35 years. All right? Anybody want to guess how long I really designed it for? Like things like, how long? 3 to 5, yeah. Yeah, I sneaked into 3, but I meant for 5. And we're going to talk about what I mean when I say designed for, right? But what we're going to find out is there's no great answers. It's all a compromise. So this is also a chance to talk to people like me because I'm getting old, I'm aging, I'm heatful these days, right? So if now's the time to ask, right? So today, how many people here are engineers? Ooh, I love it. How many people are IC engineers? Or IC designers, process? How many people are mechanical engineers? Anybody? Do you know materials, stuff like ABS, stuff like that? I'm going to put you on the spot, maybe. All right, Dr. Tremill's here. I know he's a scientist, so I'm going to put you on the spot. So, but seriously, how many times do you use a computer and there's a quirk, right? Why'd they do it this way? Well, I had no good answers, maybe, right? It's a world of compromise. Let's be real clear, especially when I worked for places like Commodore, it was about the business goals, right? I didn't put something into a computer because it was clever, right? Clever would get me fired. But if it made sense to make a lot of reliably, excellent. If I spent too much doing it, not excellent. So I had to spend the right amount of money, right? And so we find there's a price to everything. In Commodore, it was the cost of the product. When I did instrumentation, so a little bit of my background. I've done instrumentation design. I designed the Commodore 128. I was the lead engineer on what became the TED series, became the Plus 4, became the 264. And what was I talking about the C128? So you might have cheapness, but if you designed for NASA, it didn't have to be cheap, but wait a minute, it couldn't weigh much, right? So there's a coin, there's a cost to everything. And so that's what engineering is all about. So for today, we're all engineers. In this case, that only added 12 people to the group, right? But as engineers, what do? We don't look at something. We look into it. We try and figure out how it works, right? I see a chip, I start asking what that chip does. I look at a router, I know how that router is, routing, basically. And ultimately, I made mistakes. And I'm actually kind of proud of some of my mistakes, right? It's better to have made a mistake and screwed up than not to have gotten the chance, right? And my worst mistakes are the ones I'm not sure to this day if it was a mistake. Right? So in the Commodore 128, for example, in a chip, there was a register. And I said, make it go away, after something happens, and never come back. And I remember those moments when I made that. So I catch a lot of ribbing, because people want a 2 megahertz C64 mode. But I'm like, well, what if the thing we were talking about these days is the fact that C128s lock up every 5th time, and they're a piece of poop because of it. So maybe I made the right answer by doing that, but I'll never know, right? Because I don't know if I actually dodged a bullet or not. Once we have a design, it's all about risk mitigation. That means reliability, everything we talk about. And I'm going to change this up a little bit for the people that we have here than I did out east. This is a continuation of a conversation we started at VCF East. One thing we didn't know we didn't know then what we know now And we won't know what we'll know in 10 years. All right, product life, aging. Here's the thing. People meet me and they say, I love your computer. I go, well, how is it still working? Seriously, how is it still working after 35 years? And then I get the people that say, well, it broke because it's too hot. You didn't. Well, wait a minute. I can't believe it works. Well, how do we make stuff affect product life? Well, it's the materials we choose. It's how we use the materials. If I choose resistors, if I space them further apart, the resistors in theory will last longer. Well, that's how we use it, right? If I pick a voltage rating double what I needed it to be, that's how I used it. A compromise is where I didn't get to double it, I got to almost double it because of the cost. So, we design stuff in like 5 months, 6 months, a year, year and a half were typical cycles, right, of Commodore. Here's our simplified aging cycle. When things first fail, we used to call it infant mortality. I call it early failure now. It'll fail because of an engineering problem, I screwed up, or it'll fail because we didn't make the chip right. Then we get to a next group, and this is time as we come this way. So after we get out of these early failures, then we get into limited lifetime components. There are some components that started to age and fail from the moment I put them in. Can anybody think of any? Battery, capacitor, right? I knew when I put them in, they're limited lifetime, but it's a compromise. What am I going to choose besides a capacitor, right? So I could have spent real expensive capacitors and gotten fired, or I could pick cheaper ones, and you know, here we are today. And then ultimately, things wear out. They just wear out. Every computer made by mankind will fail. There's no moving parts, we think, but no, there's moving parts in these things, and we're going to talk about that. But every computer will fail. And this is where this good-natured rivalry, whatever you want to call it, came from, between me and collectors. You know, it's like engineers make horrible collectors. We throw the stuff around, we turn it on, we flip it, we short it out, because we were there when we made it. We don't care. And collectors like, preserve it. Keep it sane. Get Bill away from it, right? I told Rob Clark, a friend of mine, collector, I said, I've changed. I care about computers now. I don't want to damage anymore. He's like, I'd like to believe you. I really would. All right. As collectors, how many people collect computers where you can say, I've spent too much money or just enough money to like... So, how do we prolong the life of those? That's kind of the real conversation, right? Is, okay, we're in this boat of the parts lasted as long as they could. What can we do to make them last longer? Heat. Well, heat's the low-hanging fruit. We'll all admit it, because we all know what heat is. Everybody's burned himself at one time, I'm sure. So that's the one we recognize. And of course, we're all engineers. We know now. All of us are engineers today. There's other things. Moisture. Well, how would moisture affect? I mean, not you know, actually getting the board wet. Well, we'll find out, like those epoxy packages on chips, they're not airtight. Moisture can get through those. It just takes a while. Vibration. Guess what? The moisture goes through quicker if there's vibration. It goes through quicker if there's heat, you know? So ultraviolet light, we all know about that, right? We'll talk about that. And here's one that we are in control of mostly as collectors, is ESD. You have the ability to oh, Ron, you're here. When I said, is there a chip designer around, I was looking for you. I'm going to put you on the spot. But ESD, you absolutely have the ability to ruin your own collection or preserve your own collection. All right, I use this as an example. Gaskets. Oh, Bill, what a boring way to start. Gaskets? That's chemistry. That's waterproof. Well, I'll tell you what, if you're doing instrumentation where reliability is key, you better know about the gaskets even if a mechanical designer picked it out. I'll tell you what, if you're designing something in millions, you better know the gasket because it's going to give, you know, you're going to be responsible, you know, one way or the other. Well, look at this. My favorite, by the way, neoprene. Shelf life, 5 to 10 years. How can I design for 30 years with a 10-year shelf life on my gasket, right? So what we had to pick the best things that we thought could work for us. I want to talk about aging. Here's neoprene. I love neoprene. Neoprene open cell gaskets. Anybody use them? Familiar with what I'm talking about? Closed cell gaskets? All of these things work with cross bonds, right? These are long molecules, and we bond them together to make them stiff. And when the bonding starts breaking apart, it starts to get brittle and break. Now this doesn't have cross bonds. This is cool. This looks like a life form, right? Anybody know what that is? That's a silicon gasket. I should have used that 30 years ago. Problem was, it didn't exist. My pressure cooker uses that. Polyisoprene. Anybody know what polyisoprene is? Rubber. Well, rubber only works when I vulcanize it. When I put these cross bonds in here, I use heat, pressure, sulfur. But what happens when ultraviolet light starts to break those bonds? It gets old and crumbly. Oh wait, there's that entropy you're talking about. The movement of molecules, the breaking of bonds, and that brings us to acrylonitrile butadiene styrene. Anybody know what that is? It's fun to say, acrylonitrile butadiene styrene. That's ABS. That's the plastic, the thermoset plastic we use to make this, right? And again, same thing. We end up with we chain all this stuff together, we use cross bonds and that kind of thing. But what happens? It turns yellow. Anybody have this happen to them? How'd you fix it? How'd you fix your yellow? Did you fix it? Anybody else? Boy out east had 3/4 of the people put their hand up. They're for retrobriting. Does anybody know how it works? Does anybody know what I'm talking about with retrobrite? It's a hydrogen peroxide solution or similar, and you put it in the sunlight. And that sounds like it makes sense because there's the activation energy of the ultraviolet and stuff. Then, has anybody heard of the bromide thing? Bromide theory? If you look on the internet, you can find anything. There's a lot of people that say that it turns orangish, bromide color, because I don't want to say it outgasses, but the fire retardant that contains bromine breaks down in overage. I don't know that that's true. Who was the mechanical? The only person I would trust at this point to tell me if it's just bleaching or if it's this bromide thing is a mechanical engineer like I worked with back then. That's not the internet. The internet's a poor substitute for that guy's knowledge. So I'm still trying to figure this one out. Metals. Oxidation. We all know that one, right? What about when two metals touch each other and they're dissimilar? You get a battery. You get galvanic reaction. You get the difference in electron volt potential creates current and stuff like that. This happens. You ever see a rusty thing next to an aluminum thing or something, like bolted together with a stainless steel screw? You just made some funny kind of battery, right? This is a problem. I'm going to look at the chip guy. Bond wires, right? Where a bond wire hits it, underneath there is a strange combination of solder, compound copper and tin, and they have different thermal properties. So under the bond wire, it's pulling it in different directions. As it ages, it's going to crack, it's going to... But what's fun is looking into all that, right? Who'd think to look under a bond wire? But that's where the cool stuff is. In the old days, I used mothballs to protect my metal. UK, you can't. And you probably shouldn't here, right? Anybody have anything they use to keep corrosion out of their collection other than a desiccant? All right. Nitrogen, argon, anybody got any of that? I do at home, I weld, right? So I got welding gas. But honestly, there is something to be said about putting what you want to protect in a dust-free environment, maybe without any of that pesky moisture and oxygen if you can live without it. So by the way, shout out any questions if you have them live. Let's stop me there. If you hear me say something wrong, definitely stop me. Because that's the biggest thing. Yes? Yes, I need to do that because watching the old video, you see me go like this and it looks like I'm having a stroke and I'm just listening to a question. So, all right, limited lifetime components. These are the components I knew when I put them in wouldn't last long enough or wouldn't last forever, right? So in the old days, how did you store information over a reboot? We didn't have flash, right? So we had battery backed up stuff. Anybody recognize this? Have you guys torn into enough boards to recognize the little, I loved that thing when it came out. Because I used to have to use NiCad batteries that I soldered to the board. I used to have to, I needed analog comparators, and I needed CMOS to run it because it stayed powered up. And by the way, and then this came out, and I was in heaven. Forget that it only lasts 5 years. I was in heaven. Now, when I do instrumentation, I'll send a tech out to replace it. But there's no way something like this would have ever made it into a Commodore. Now, as things like this came out, we were learning the hard way. For example, we would take a battery, put it on the board, put it through the drag solder machine, and it would short out the battery for 8 seconds while it's in the solder, right? Well, duh. Made sense, but only after you figured out what's going on in production. Here's other problems with batteries, right? This is what they're supposed to do. This is their chemistry. So we shouldn't be surprised when they leak. I was just telling somebody today, the Commodore LCD computer still has the original batteries in it. Jeff Porter never took the batteries out. So that's a Porterism for you. Here's everyone's favorite. Anybody like these things? Anybody hate these things? Why do you hate them? Why don't you like them? They're limited life. I knew that. What was my choice, right? So the problem with capacitors, if you can see, this is bulging, and see here's this little black plug pushed out of the bottom. I don't know if you can see it. See, this is bulging, about to go, but those ridges are made to be, rather than have it explode randomly, they want it to explode in a certain way, and then here it is after it's done it. It's supposed to. That's how these work. They outgas, right? You can't have heat and a lot of movement of charge in chemistry without some kind of reaction occurring, and this is what they did. Now, before we had sealed versions, because we always say, oh, the dielectric dries out, right? You all have heard of recapping. Well, when the dielectric, in the old days, this wasn't sealed. And we know that because we'd stuff the board with them, put them through the drag solder machine, then put them in the dishwasher, spray them with water, and we'd actually wash the dielectric out of them. So we were ruining them again. So we went with sealed ones. This is not a perfect seal. There's no such thing as a perfect seal. Capacitors will break. That's what they do. Any questions about capacitors? Anybody ever reconditioned a capacitor? Anybody know how capacitors are made? How's a capacitor? What's in here? Yep, layers. Yep. Right. So, remember I said it's how we use materials? The bigger the surface area, the more dielectric, the tighter it's sealed. Those are all things we can affect. My thing I could do is I could double rate a capacitor. If I needed 25 volts, I'd get 50 volt capacitor. Why? That'd make this bigger. There'd be more plates, there'd be more dielectric, there'd be the ability to get the heat out. Capacitors have lifetimes. I never did that calculation, I didn't need to. I can look it up. But just know that there was math there. We weren't, this isn't something where you stick your finger in the air, and there's reliability engineers that this is what they do for a living, if they're good. If they're bad, they just BS their boss. So here's how we fixed early failures. Hey, Ron, don't you guys, when you rev a chip, you're not only revving it for the logic problems, right? If you want to correct an IC design, you do a revision on the chip. At the same time, at least in our MOS, the process engineers were also putting their inputs in. They're like, get this out of the shadow of this gate or something like that. Yeah. So we worked our asses off in the early part of the design to get you out to here. And that's where all those revisions of chips came from. Now, back then, we didn't have the tools we have today. And I could talk afterwards about that a lot. Everybody recognize this? So, here is where failures rise up out of the noise, and we start to know that the failures are starting to wear out. I use 2 sigma, it's called. Some people use 1, some use 3. I call this like the 3 decibel point. Like, it has nothing to do with decibels, the 3 dB point, but it's where the logarithmic curve starts, right? And I've hit that. So at Commodore, and I hate to keep saying them, but at consumer-based companies, we would typically put this at the 5-year mark, right? Now, it didn't mean it's going to fail right at 5, but statistically, the mechanism is they're wearing out. They're starting to wear out. So do chips wear out? Yeah? There's no moving parts. Ron, do chips wear out? How? Well, let's see if I got them all. Because we think if the chip, since it can't wear out, there's no moving parts, it must be because you used it wrong. No, chips get old. You know what? They get old just sitting, right? It doesn't even have to be turned on. So, but what's to wear out? Boy, I don't like having this and that. I'm going to keep going back and forth. There's nothing to dry out, but there is a dielectric. We'll talk about that. So here was the conclusion that I ran into on the internet. I actually unfriended one person in my whole time on the internet, right? This guy kept hassling me, telling me that because chips can't wear out, we must have built them really bad if they're breaking 35 years old. And he assumed this because he thought he understood heat without knowing what heat probably really is and how it affects a part. And the proof he offered was that we didn't even put heat sinks on CMOS EEPROMs. Well, CMOS EEPROM doesn't need a heat sink. How many people here put a heat sink on one of their old computers? Why would you do that? Why? Dissipate more heat. You want your computer to last longer, right? It seems like it couldn't hurt, and I'd argue it probably doesn't hurt. So why wouldn't you do it? And I can't argue with that. But it doesn't mean that it needed a heat sink to get to this part. And there is actually times that could hurt us. When we made consumer products, we had the FCC to deal with. EMI means electromagnetic interference. There it is, the noisiest thing known to mankind at the time, sitting next to your TV set, and we're supposed to protect you from it. So we put on these big EMI shields. You've seen them, right? Well, as soon as I put that shield in there, by the way, that shield cost me 40 cents in quantity. I love that big shield that's in my computers, right? Because it hides all my sins. I didn't pass FCC by being a great designer. I passed it by being a good designer and having an EMI shield. But wait a minute, it's going to heat my parts. I've created an oven, right? So what do? Well, my mechanical engineers, they just made little tabs. They made it into a heat sink. So the thing is, if you have an old computer and you take off the EMI shield, you might be taking off the heat sink. So that's fine, but then don't yell at us. I took off the heat sink and it's hot. That's how heat sinks work, right? Now, again, there's still compromises. Semiconductor wear-out failures. Time dependent, dielectric breakdown. You probably thought you'd never hear that again in your life, right? Hot carrier induced character. Oh, I love hot carrier. Sounds cool, right? I can just see it. Electromigration. Uh-oh, something's moving. I see the word migrate. I'm not going to go into the math of reliability, but I want to show you something. This is the Weibull distribution. Weibull is one of like 3 or 4 different ways for statistics for aging, right? And somebody else would do the math. But what I liked about this, hopefully you can see this curve. By the way, you can make these numbers into anything you want by changing the variables, right? And so people don't know what they're doing, make it, you know, here boss, I made the numbers match. There's Dilbert comics about that. But this is interesting because it shows around, if I take this as 5 years and 15 years, around 5 years, the failures really start, the wear out failures. At 15 years, assuming a normalized curve, they kind of stop. Why do they stop at 15 years? They're all broken. Right? They failed. We're running out of them. Boom. Right? Now, there is a real long logarithmic, you know, out to here, and that's what the collectors are using. Is like that 3% in my mind that's left. And again, I'm going, how are any one computers working, knowing what I know about every, you know, a pile of 1,000 components in it? So another way I see, this is one everybody, this is what they focus on. The thermal acceleration factor for IC failure. Yes, temperature matters. Don't let me tell you it doesn't. But if you don't know, but the way we really worry about it is something called Boltzmann's constant and the activation energy. And if you can do the math right, and you can do it wrong easier than you can do it right, you'll actually figure out what the life of that chip should be. And by the way, when I talk about heat again, you know, we think of heat as when it's running in the computer, right? Somebody just measured a +4 TED and it was running at 40 degrees C. Well, that sounds hot, right? I'm 37.5 or so, you know, body temperature, 98.6 degrees is just around 40 degrees. So it's not that hot. But wait a minute. The difference between at rest at 30 degrees C, room temperature, and 40 degrees C, I'll tell you that even at room temperature, your chips are getting older, right? Just not as fast. So people forget that heat doesn't mean heat above room temperature. It means heat above absolute zero, actually. Now, there's a rule of thumb that says, oh, for every 10 degrees, you double, you times 10 or something. Well, yeah, you can take these rules of thumb, and by the way, rules of thumb are only useful if you know what the rule of thumb represents, right? It's a trick so that you can get the design into your head long enough to think about it. But you better still know why the rule of thumb exists. And if you don't, I call it squinting. If I look, oh, between here and here, I can get it to go. Well, yeah, if I squint and look, I can make it do that. It's better to know why the heat affects it. And by the way, there's 1,000 components you have to add up all these signatures for, right? Heat. Everybody knows about heat, right? Everybody's burned their hand. Conduction, radiation, convection. Which one's the best one? Which one's the best one? Anybody over here? What's the best way to get heat out of something? Why do you have a heat sink? Conduction. Conduction's most efficient. Radiation and convection assumes you have something, and conduction, that you can radiate or convect to. Radiation is where it's called black body radiation. It's just where it radiates the energy out into space and it takes the heat with us, whereas convection uses air, and the heating of air, as the air moves, it moves and will rise, and more air comes in, right? That's how a heat sink works. Well, wait a minute, if I'm relying on convection, I'm kind of behind the curve in my mind. As it turns out, the primary heat sink is the PC board. 60% of the heat or more will leave via the PC board. So when this young man told me that we didn't have heat sinks on the CMOS EPROMs, well, actually we did. It's the PC board. Why does that work? Well, this is a lead frame. And we used to use beryllium copper lead frames. We went to them to make the VIC chip stop sparkling in early Commodore 64s. That's conduction. That will take that heat out of there much easier than conducting through the epoxy to the heat sink, which then has to radiate. And here's our problem. If you do open a computer and you put a heat sink on it, you're inside an enclosure. You're heating the air in that enclosure. Well, what if the chip was cooler than the air to begin with? Now the heat sink's taking heat out of the air and putting them into the chip, right? Heat sinks work when there's a place for the heat to go to. Heat sinks inside a closed container ultimately will reach equilibrium and they become useless. When I have my big EMI shield, I'm conducting it all the way to the edges of the board, all the way to the edges of the housing, to the world. I'm conducting it to the environment. Where, as opposed to this thing kind of heating this little air above it here. So, you asked about the VIC chip. You asked me a question. Leonard Tramiel here asked me a question. Unfortunately, it gets back an answer this long about heating of the VIC-20, right? Because what did he say? He said it took 2 or 3 hours to heat up, but then you had to put ice on it for over half an hour or something to do it. And so I'm trying to figure out how something could take 3 hours, and yet if I put ice on it, why doesn't it start working again right away? Well, there's something wrong with the description. There's something wrong with the model, right? And we can calculate this. So this is my bread and butter here, is telling you how hot the chip will get, not just here, but inside. That's all math, right? By the way, I'd never been to college for any of this. I picked this up as I went along, but I worked with really bright engineers. And so I really wasn't self-taught. I learned from them. So there is something about the temperature that does get me going. Thermal cycling. When does a light bulb blow out? Usually when you flip the switch on, when it goes from hot to cold, that thermal shock, when does a drinking glass break often? In the dishwasher, or you take it out and tap it on something, and there's a flaw in the glass, and that's when it breaks. Well, guess what? Chips are made of glass, right? So the flaws that were there for however many years, you heat and cool, shrink and pull. That's what does the damage, in my humble opinion, far more than just heat. Again, it's already hot sitting in the room. It's just, so I came up with this. I wanted to build a project that would have a little, we used to call them phregistors, right? Little thermoelectric coolers that actually preheated your chip, right? That actually would bring the chip up to its nice ending temperature. And this way, when you turn it on, instead of going boom, right? It would go, okay. People hate that idea. They don't want to preheat their chips. They're because it sounds wrong. It sounds like I'm going in the opposite direction. But truly, if it was a little phregistor, I could preheat it and then flip the polarity, and now I'm pumping the heat back out of it. But I'll probably never do it. But and what collector wants to be the guinea pig, right? Who wants to risk the 3 they have or the 1 they have to try that? So here's what I've been kind of going on about. Age is what kills these things, and it's accumulative. So whether I'm heating for a while at 28 degrees C and then 45 and then 28, the problem is it's still accumulating. So to me, there isn't a huge difference between aging when it's hot, when it's at room temperature, and when it's at when it's operating, when it's got power. This one's weird. A chip will wear out just because there's an electric field, right? Wait a minute. Things wear out because of current. Current is power. Current's the verb, right? We're used to light bulbs blowing out because there's current flowing through them. Voltage is just an opinion. It just sits there. Not on chips. Just the voltage sitting there can wear them out. Why do I mention this? Because there's so many more things than heat that breaks these. Just the age that the voltage. This is like, do you remember Franklin had that experience, lightning or whatever, and he may have had the Clyde jar with the 2 gold things that separated. Well, picture that a year later they're not as separated. Well, I wouldn't expect 2 gold leaves to wear out. And we go in, we'd find something changed, right? Something corroded. But that's what chips do. They wear out with electricity, with a electrical field. What's this? Anybody recognize that? Oh, come on. Yeah, you do. Okay. The chip designer in the back recognizes ESD damage. How does ESD damage work? And you should, as collectors, as engineers, we need to know this too. Does it blow it out right away? Sometimes. When you get a big old arc that you can see, maybe it blew it out right away. Usually what it does, though, is it makes a pinhole. Looks like a little meteor, doesn't it? What happens is things start getting impure around here. It starts heating. It starts unevenly expanding because the heat starts corroding, and it just builds up. So an ESD problem, an ESD insult, may not show itself till months later. Not a year, not often, but months later. The way we troubleshoot ESD in production is we have to look at processes. It's statistics, right? We had one issue at one place where 1 out of 20 EPROMs was failing. 1 out of 20. Boy, that's a round number. I don't like that. Turns out the assembler, when she would go to pour them on her desk to load the chip inserter, the ESD on the desk wasn't as good as it should be, and the very first chip out of the tube, the very first pin on the corner, would hit the desk and take the charge off. So we were breaking the first chip out of each tube. We can only fix that by looking at the math and then going backwards and finding somebody's got a broken strap or something like this. But as collectors, you guys should be using anti-static precautions. Should be using your bags, should be using your straps, if you care about your collection. Me, I don't care, I just throw them. I think it's funny when sparks shoot to them. Time dependent, see, this a lot, the Eastern crowd loved this, by the way, but you guys aren't quite as much into chemistry. Yes? Okay, so right. Ultimately, I think the question is, with more dense chips, is ESD more damaging? Isn't that a way to? Well, picture instead of it taking out just this valley, that it took out 18 transistors because they're smaller, right? So yes, the features are smaller, so the damage is greater. The features are smaller, so the breakdowns are less. There's all kinds of, when we go, and so the VIC chip in the Commodore 64, if I told you a Pentium has 5 billion transistors in it, 5.5 billion, you could have one transistor, 5.5 billion IC engineers each do one transistor. It's mind-boggling. The VIC chip in the Commodore 64, anybody want to guess how many transistors were in that? I'll let you, how many would you, or in one of the LSIs of the day that you did? Yeah, 270,000 are in the VIC chip. Yeah, and as low as my MMU had 90,000 in it. Yeah, and then they would hand check them. They would sit, you hand checked with scales and stuff, right? So here's the thing about chip design in the 80s. We didn't have an electrical rule checker that would take your schematic and say, yeah, you built the chip right. He was the electrical rule checker. They would print plots, take a schematic, and then they would sit there for months with a scale measuring the geometry of the polygons to match the schematic. You could be brilliant, but if you couldn't sit for 4 months with a cold cup of coffee doing this, your chip might not work. So the guys that were both of those were the best chip designers. We did have a rule, we did have design rule checks, which said in production, if metal gets too close to each other or something, it'll flag that. And in the TED chip for the old +4, the 264 series, when I first got there, we couldn't turn the chip on. Well, right, and then the next one, we could turn it on, but it would stay in PAL mode. We couldn't write to it. Well, what had happened was A9 went like this, A8 went like this, the address lines, and then A10 went right across them, shorting them, and then right across them, shorting them again. The address lines are shorted together. You can measure it with a meter on the pins, right? Well, how does that happen? Well, they didn't get too close. They were a complete short. So the way they actually got the chip to work to where they could test it, because it cost us almost $500,000 a run, but between $200,000 and $500,000, depending on how you're doing it. So these guys put it under a microscope and turned the light on. And they used the photons hitting it to write to a register as if the address lines weren't shorted, because they really wanted to know how bad NTSC mode was working. So it's like, wow, we're using photons for troubleshooting. So basically all time dielectric, I'm skipping it. It gets old, it gets impure, it messes with the geometry of the gate directly under it. But here's a variation on it. Hot carrier injection. In printed circuit boards at high speeds, I'm not working with electrons, I'm working with electric fields, electromagnetic fields. They go rushing at close to the speed of light, 7/10 the speed of light. They turn corners at a dime because they have no mass. But inside of chips, it's electrons, it's carriers, it's holes, it's ions. Have I missed one? That's ions, carriers, and electrons, right? Well, when these things go flinging, here's a transistor, by the way. Here's the drain and source, and here's the gate. And under there's a channel, and as these electrons go racing through this channel, they couldn't make the corner. They'd embed themselves in either the dielectric or something else, and that's called hot carrier injection, because it was a hot carrier. Well, that contaminates it. So they have tricks these days. They'll dope this one different than this and stuff, but this is another example. This is what breaks CMOS EEPROMs. Not heat, statistically, it's these things, because in an EEPROM, this is floating, right? We wrote to it with a real high voltage, and then we hope that charge stays there forever. Well, if you got these guys banging into it, it's going to drain your charge off. Here's one, this kind of electromigration. Since electrons move, guess what? They take atoms of metal with them, right? Metal will move. There's whiskers too, you may have heard of that. You may have seen the metal grow. Here's a good one. The current through this track, this is a microscopic shot of a chip, all these have been, scooped the metal out of here and deposited it there. I'm going to assume that there's kind of a standing wave here too to affect that. But think about that, the electrons moved my aluminum. It's not heat, it's electrons. Another failure, heating, cooling, it cracks. I could talk for days just on that. Soft errors. Well, we didn't have flash memory back then other than EEPROMs, right? But a gamma particle, for example, was another form. And I throw this in just kind of because I thought it was interesting. The way we fought gamma radiation back then, screwing with our chips, was we used RTV. Because of the cross bonds I've been talking about, help block the gamma rays from getting to the cells. So what happens is, here's a gamma ray comes in, bangs into this thing. He says, by the way, I'm charged like nothing else. And it will screw up either the structure or the contents of the structure. Right, there's an EEPROM. Exactly what I've been talking about. Floating gate and things getting up in there. Anybody ever see crud crawling on your PC boards? Has anybody ever had to clean a PC board as a collector or anything? And what was on the PC board? Dust? Oh, let's talk dust. Dust isn't bad because of what dust is. Dust is bad because what dust brings to the party with it. It brings grease, dirt, mold, mildew, moisture, all that. I used to be a TV repairman when I had my license at 17. Dirtiest thing known to mankind back in the 70s was the inside of a TV set. Things were ooky, dusty, and you could tell a lot about the family by looking in the back of the set. If they had little girls, there'd be barrettes and, in there, there'd be balloons if they had kids, pennies, all kinds of things. One time there was like a bag of weed in there, right? And it's like I'm standing so my boss can't see, and I'm going like this to the guy whose TV set I'm fixing. I want him to go around and take the weed out of the... So we knew a lot about that family. So yeah, dust is bad. This is why we say a dust-free environment for storing your stuff in really is important. That's not just cleanliness. You get the right material here though, and this happens all the time everywhere. The world wants to come to a state of equilibrium called entropy, right? We all know that. This happens everywhere. Stuff wants to grow in one direction, it wants to ruin your collection in the other, and you will actually see, like, silver is bad for this. This can happen in a chip. When I opened my old LCD computer, rust had grown. It had probably, you know, it'd probably done a galvanic reaction. Let's talk water. You know, chips are in those little black hard things, right? That's watertight, right? No, it's just epoxy resin. It seems to be watertight the first couple years, but not 35 years. It's just time, right? And so water can penetrate through your epoxy if you store it in moisture. And they'll come in through the lead frame, near the lead holes also. And they'll leach right in here. And here's all kinds of pictures. You can see where it gets into the chip and messes with it. Now, is anybody familiar with the PLA problem of the old Commodore 64s? What was the problem? What? No? Anybody else? Is Beth here? Oh, it's probably before time. Okay, Ron! Ron, what was wrong with our PLAs? Do you remember? Okay, so here's what I'm... Yes. Yes, we fixed it before your time, thank goodness. They weren't lasting 3 months, and you can actually put them under the microscope and see what's wrong. The PLA is one of the main glue chips in the Commodore 64, and we stole it, right? I'd walk in the hardware lab, and up on the wall were Polaroid pictures of the Signetics part. And here's the guy entering them into a computer so we could make our own version. We didn't get the passivation layer right. There's six, in old NMOS, there's 6 layers plus a 7th for passivation. Passivation is just like a conformal coating. It should be the easiest thing. It caused the purple, was it purple or green? It was purple, the crud. Yeah, somebody else. We called it the purple creeping crud. Well, it turns out we had too much bromide. Now it's bromide. We had too much bromide in the glass, silicon oxide, silicon nitride is a form of glass, sort of, right? And I thought it was because the valleys would get too thin or something. No, the bromine was the wrong amount. It took a metallurgist and a glassurgist to figure it out. So when water gets into these chips, not only do you get this junk, but if here's a transistor and there's more ions from the water penetration on one end than the other, this transistor's not working right. It's off kilter, it's tilted, it's, you know, it's contaminated on one end. So water is a nasty thing. So again, keep your collections with desiccant, and I'm required by law to tell you not to eat the little packets of desiccant, right? I feed them to my dog, no. I feed them to the neighbor's dog. So why not store chips in the freezer then? Bill's going on and on about, you know, room temperature is a temperature. Why not why not store in the freezer? Anybody know? What? Oh, different thermal, oh, it's amazing how bad the different thermal expansion coefficients are, right? I don't think you can put a chip designed for, that isn't designed for minus 10 degrees. You can break it that easy. What happens is the thermal expansion of metal and beryllium copper and the epoxy and this, and even the chip die itself are all expanding and contracting at different rates. Well, way out on the corners of the die, it's the worst, right? It's like a bridge where they have those breathing things, you know, and you see them moving more on the, so you get what you call peel on the corners. It's where the chip goes eek and gets smaller, but the metal part stayed the same or the die stayed the same, so it peels it off. So shoot, I can't even put them in the freezer, right? How the heck am I supposed to keep this stuff working for 35 years? Well, here's another reason you can't put it in the freezer. That epoxy resin stuff, that's got junk in it. The cheaper it is, the more junk. Everybody remember when does anybody remember when the epoxy plant for the entire world burned? and we couldn't get DRAMs for, yeah, well, it turns out only one company, Kyocera, was making the epoxy for this stuff. What's that? Oh, was it? I thought it was 100. Okay, 80 to 100%. Yeah. Right. Yeah, there had to be other sources, but not sources that could support the supply chain. Right. So what happens is if I freeze this will shrink in this direction and push a piece of scrap down into my chip. Oh, shoot. I can't keep it in the freezer. How's this stuff working after 35 years? Oh, there you go. I figured out how they're working. Don't laugh. It's working because you've been fixing them. I didn't think about that. I'm an engineer that sold you a unit. When you tell me your unit's still working, I'm not thinking that you took 4 to make one work. Yeah, I believe that. And in a couple of years, you're going to need 6 to make it work, right? So the issue, and I talked with, again, my friend Rob Clark, he said, yeah, 70% of the TEDs I get are broken when I get them. I'm like, that I believe. Okay, thank you. I'm not off in my own little world. This stuff, statistically, all the layers of parts, there's something broken in there, but if we swap out a couple, okay, it works again. So here we are, 5 years. Here we are at 15 years. Here we are, 35 years. And I can't even see the logarithmic tail on that, right? So when somebody says, you must have designed it wrong because it only lasted 35 years instead of 38, I'm like, no, I was only supposed to go 5, man. Seriously. If you make it 35 on my budget, and I've had people, again, who are into the clever. I had somebody they were irate with me. You should have put a switching power supply in the +4 series, the TED series, and it should have been a fan. And if that person had gone to my boss, Shiraz Shivji, and said, we're going to put a fan in this $49 thing and this, I don't know what Shiraz would have said, but I know the tone of voice he'd have said it in, and it would have been, are you frickin' nuts type tone of voice, get out of my office, and you wouldn't have been on that project, right? So the guy that told me how to do my job, he wouldn't have kept his job, right? Because that wasn't the business we're in. We're in there to get it, as cheap as appropriate. So yeah, we're way out here, and we've been fixing them. So that went a lot faster because y'all didn't throw things at me as much as they do out east. Is there any questions? About what? Yes. Right. Yes. Now, so even today with surface mount, yeah, thank you. So the question was about more modern parts, is that fair to say? Oh, for years. If it wasn't, yeah, if it wasn't stored in a pretty dry thing, it will have absorbed, what? Oh, okay. Yeah, and these days with surface mount, if you're not going to use them right away, you're supposed to put them in a dry storage because that's how fast small parts can leach it through the epoxy and through the lead frame. So I actually have a bin at home that I throw, if I'm not going to use my surface mount parts right away, I throw them in there, forget they're in there, go and order more, throw them in there too, and pretty soon I've got 4 times the number. But so, yes? You're right. I normally talk about the whiskers where I showed that growth. External, and see, I think internal and external kind of equally, right? But yeah, whiskers are, molecules want to move, right? Everything's warm, and warm means motion, and motion means move, and whiskers can occur. I've heard of entire data centers going offline because somebody ground up some zinc or something in the room. It becomes an airborne dust, very small particulate, And because of the electric fields, they will start to grow. And then I think there's a chemical thing too. It says, oh, by the way, if you're my kind of molecule and you get close, let's just stick you on too. And I wish I could tell you how to mitigate it other than dry, moisture-free, but having dust for, in solder, you said? Leaded solder, yeah. And that's why I was talking about the bond wire, where even under the wire, it's combinations of lead, tin, you know, all those things in various compounds with various thermal expansions. So, yes? Oh, yeah. There's an engineer's vision of how things are. Even a glob of solder is not simple. And yes, a glob of solder is an amalgam, and probably the best I could call it. But it's different. There's, I can see the chemical compounds, but they're all slightly different, all slightly the same. And yeah, there's different. Yes? Go ahead. Yes, you. I'd make it out of rock or something. I'd make a big abacus and move the rock, because I don't know how to design for 10,000 years. I don't, because you know, what do? You store it in a vacuum. Well, wait a minute, whiskers grow in a vacuum. You know, so I don't have a good answer. But the very first thing I would do is try and solve the thermal equilibrium, the different thermal expansion issues, and then I'd take it to a real low temperature or something. You know, I would try and minimize voltage, minimize heat, and of course the environment, no moisture, dust and stuff. And even then, I think the chips are going to wear out just because they're an electric field. So now we get to use 1 volt instead of 5, right, for our chips, or 0.8. That should help, but the answer is 10,000 is unbelievable. Every computer in this building will be broken in 10,000 years, I believe. Maybe even unrecognizable as just heaps of rust and some dirty glass in there. By the way, somebody once complained about the VIC chips, how many bad ones we made. And the answer was, they said we could pay between King of Prussia and Norristown with bad VIC chips. The guy just goes, they're just dirty sand. They're just, I mean, we didn't care. We needed to make more to get the good ones. We didn't care about this crap. I'm sorry, who else had a hand up? There's oh, you know what? I'll have to check it out. We'll see if I agree. Yes?
Commodore 128 power supply cords.
Yes.
You ever had a greasy one in your house? What do you do about those greasy cords?
What do you think causes the grease? Something breaking down. That's it. It's a byproduct. It's coming out of the core. I don't know that you can, because it's not like you can wipe it off. It's coming out of the butyl rubber or whatever. Temperature, moisture, you know, it's the same culprits. Honest. And vibration, I'll bet if you took that core and vibrated the heck out of it for 560 days, it'd be greasier. I honestly do, because you would exercise those molecules and break the bonds and things. So I haven't had a greasy core. I've never been even accused of having a greasy core. Yes, sir, you. Yes, please. The most surprising what?
Surviving part.
So the question is, what's the most surviving part I can use? Right. Oh, the HMOS versions of the TED chip that's in the 264 series. So here's why. You've all heard the 6502. Old, mature, NMOS process. They had years to get it right, and they licensed it out. And then we come along, and we make this 7500 series called HMOS 1. You remember HMOS 1, right? It's a shrink plus some tweaks, right? But it's a shrink mostly. This is like baking a cake when you make an IC. They would make the runs, whole runs. So, by the way, I worked above MOS. Who made our chips. It was like working above magicians, right? I mean, everybody else, Apple, used our chips, right? We made our own. Atari made their own too, so TI made their own, but we won't talk about them. And I forgot the question. So we worked above the, I worked above MOS. What was the question? I'm sorry. HMOS, thank you. See what happens, aging and heat, mini strokes. It's called a transient ischemic attack, TIA for short, and I've already forgotten what it was again, HMOS 1. So in the middle of this, we're doing these shrinks and stuff, and it really is like baking a cake. They would change a parameter or two, and they would plot them called shmoos and stuff. Anybody old enough to remember a shmoo? And an entire thing would fall on the floor, and by that I mean the yield on the run would be so low, it's not worth putting the ones that work into packages, plus they'll probably fail too, right? So we tweak something, we run it again, and we're trying to make our batches smaller now because we have to still tell our bosses why we're spending money. But eventually they get the recipe right, and every time we would stop doing one chip and start doing another, there's a little ramp where we'd make some dirty glass trying to get it right. Well, so the HMOS 1, I'm surprised they're still out there, but Rob Clark tells me he's got a whole bunch in his TED series is still working. So the answer, and then HMOS 2 even more so. And then I did have that young man come to me and says, oh, the 6502 doesn't break like the HMOS 2. You made the HMOS 2 bad on purpose so you could sell more parts. And I went, unfriend, not talking to you anymore, because that insults my friends, right? So that's the part, though, was when we changed processes, changed recipes, and yet we're cutting it. I mean, who else was doing this back then, right? So, what else? Who else? I saw at least one. Yes? I can't hear, I'm sorry. Oh, a horror show for collectors, yes. Guess what? Welcome to being an engineer, we're paranoid. There's no good answer. I go to sleep worrying about what. Go ahead, Don. Okay. Okay, so you just asked for I heard every third word. I'm going to reconstruct it and say you're asking for the short version of how to protect your stuff. Right. And it's no surprises. Temperature stable. Stop the thermal expansions. You've seen how bad they are. Dust free. If you can put them in carbon dioxide, I mean, you know where you can get carbon dioxide? Well, you can make your own, right, with the vinegar and stuff. You know, in other words, there are sources for, I really do have a can of argon in my thing from TIG welding. So moisture, heat, even light, static. So basically it's the common sense thing that we're talking about, but do it as a true effort. You know, really find that good place, seal them up, don't open them and not seal them tight, things like that. That's your best chance, and then they're still going to fail. You know what, they might fail 6% slower, and 3 years from now they're still, you know, it didn't matter, they still failed. Yes? Yes? Was it ferrite memory by any chance? Okay. So some technologies weather better. That's probably a bipolar technology. Would that be fair? Those are transistors, junction, BGTs. When we went to the magic of MOSFETs, we said, here's a conductor and here's a dielectric. Boy, this word dielectric keeps popping up every time there's a failure mechanism because we want this nice thin insulator. Well, thin means something could poke through it. So when we went to MOSFETs, we made a compromise. We said we can go smaller, faster, harder, and it won't be as bulletproof as a light bulb and a switch or a BGT transistor and ferrite. So, yes? It's going to last longer. ECL will, yeah. And they don't suffer from hot carrier injections the way they have other things they suffer from. Surprisingly then, the mechanical, because they're bigger, you ever I've dropped a TO3 case transistor and it rattled when I picked it up. Bigger die means bigger features means more vibration sensitive or G-shock for. So again, not perfect. I mean, a small CMOS will handle G-shock better than a big old BJT. So, anybody else? Anybody? Oh, y'all heard of Commodore, I heard that part. What's your favorite computer? Anybody, go ahead. We're not religious here. What's that? Mega 4000, designed by Greg Berlin. I thought somebody'd say TRS-80. That was popular back then. So, all right, if there's no other questions or anything, again, I appreciate your time, especially as an old aging engineer talking about old aging stuff. I'm Bill Herd, and it's just been wonderful being with y'all. Thank you.